Hello and welcome everyone to TWSS 2021, TechX's annual user conference that we have. We've had a great event so far. We've had guests now from 17 different countries join us. And I want to thank all of you who are here today for this talk. It's pretty neat. These are actually Salvador and Trudy are users. They don't actually work for TechX. They are users of our product. And so they will be speaking tonight. I'm going to give you a brief bio on the two of them. Trudy is going to be speaking first, and Trudy Bolin, she earned her BS in 1995 and MS in physics from the Illinois Institute of Technology in 1997. She has 12 years of synchrotron experience as a beamline scientist at the Advanced Photon Source located at Argonne National Laboratory, and 18 total years of experience at the facility. She served as a senior researcher in the Department of Electrical and Computer Engineering Group at Colorado State University from 2015 to 2017, and she's attended numerous sessions of the United States Particle Accelerator School. Since 2019, she's both a Ph.D. student and research scholar at the Electrical and Computer Engineering Department at the University of New Mexico, Albuquerque, New Mexico, USA. She is currently using numerical simulations to design RF cavities for hard X-ray free-electron lasers. And she's serving as a member of the NA-PAC 2022 Local Organizing Committee. I'm going to introduce Salvador as well, so then we can just go on and speak. Salvador's bio states that Salvador is a Mexican physicist. He received a BS in physics from the University of Puebla in 2012 and a PhD in physics from Old Dominion University in 2018. His graduate research at Jefferson Lab focused on superconducting crab cavities for the electron-ion collider. He's now a postdoc at the University of New Mexico, exploring applications of artificial intelligence in the control of particle accelerators. So wow, I love those bios. So Trudy, I understand you're going to be speaking first. So thank you. I will pass it over to you.
Okay, can you hear me?
We can. You sound great.
Great. Okay, well, thank you very much for the nice introduction and for the chance to give us an opportunity to present some of the work that we're involved in. So the title of the overall talk here is a use of VSim for design and advanced controllers of RF particle accelerators. We have a fairly large author list. Sal and myself and Sandra Biedron are from University of New Mexico. John Carey is from TechX. Massimo Del Forno is actually from ViewRay Incorporated. He used to be at SLAC in California. Mark Curtin and Bill Hartman, Tim Purnell and Don Swenson are all from ILS. And these are some of the people that are involved. TechX, Element Era, which is a company owned by Sandra, and ViewRay and Ion Linux Services. Okay, next. So I already touched on a little bit of who we are and the presentation goals, but one thing I really would like to emphasize about Sandra's group is that it's very diverse. Okay, so we have people from very many countries, many backgrounds, many skill sets, and we're making it work. We all try to contribute our own thing to each project, and I think it's been it's a lot of fun. The research is also very diverse, as I just said. And so there's multiple members of the group that either use VSim regularly or work on a project that's going to be involving VSim in the future as part of the simulation work for modeling. So some of the projects that we're going to talk about this time involve high frequency novel accelerating structures, which is what I've been primarily working on. That's the dynamic mesoscale material science capability, which I've spoken about before. That's at Los Alamos National Laboratory. And then AI-based machine learning controls for particle accelerators is going to be what Sal's going to be focusing on. And that includes proton-based cancer treatment. And that would be Ion Linux Services systems in Albuquerque, New Mexico. And actually ViewRay, they do cancer research too. Next slide. So high frequency novel accelerating structures. Next. So Marie is matter radiation interactions in extremes. So according for several years now, there's been conversations around out there about what we need from a beam in order to advance science. So according to some private conversations down here, there's a manuscript that's being prepared. It's Sandra Biedron and Stephen Milton. They were talking and said that there's tight beam quality restrictions and small space that's actually available makes a pretty challenging environment in order to meet these goals of exploration and advanced accelerator components and compression techniques. So Marie is a proposed XFEL at Los Alamos and could go up to about 42 keV. And that adds a suite of tools for scientists to use in extreme conditions, such as the one depicted on the right here, where we show an explosive as it's igniting. So we've actually gone from explosives and materials that could be used in that manner to cancer research, all with VSim being involved. So that if you don't get it diverse, I don't know what it is. And we also are talking about a liquid neon cooled Cband injectors, 45 Kelvin. And coupled with other compression techniques, they could have a great promise for helping solve a problem for XFEL Linux at Marie. Next. So, dynamic mesoscale material science capability. So let's put these two things in relationship to each other. We have Marie, which is the matter radiation interactions in extremes. Marie is a specific facility concept that would comprehensively meet the DMM-SC capability gap. Now, the pictures I showed on the slide are actually from a presentation from John Sorrell, laboratory director at Los Alamos National Laboratory. And he gave this, he actually said that line during his talk, and it finally put things into like a real focus for me about how one relates to the other. But one thing you notice about this picture is that this facility is large. I mean, it says it's built on top of a mesa. And at 12 GeV electron beam, we can get 42 keV of photons, which is going to meet research needs, say for, you know, in this size regime. So we're at 10 to the -6, we're on micron scales here. We could look at defects in interfaces and phase separation, emergent phenomenon, and so on and so forth. So this is a great opportunity for everyone involved, but it's real estate. Next, please. And real estate is expensive. So I wanted to talk about Cband accelerator cavity design. So free-electron lasers in the soft to hard X-ray regime, as I stated, enables new developments in broad range of disciplines. So you need a higher electron beam energy capable of generating the higher energy X-rays. So as a consequence, your length becomes longer. Your costs quickly become prohibitive, and then you have to turn to state-of-the-art accelerating technology. Cband design is an idea out there because it can give us the type of beam that we would need while still having a desirable quality of not taking up too much room. For example, we have RF bands here. We have an S band, 2000 to 4000, a C band, 4000 to 8000, and oops, back, please. Okay, and an X band, 8000 to 12,000. And the C band is pegged at 5712 megahertz or 5.712 gigahertz. But your cavity radius when you're at C-band design regime you have to note this is inversely proportional to frequency. We have a high gradient of acceleration, and we're trying to put it in a compact structure. Cryocooling will help aid in this, 45K. That will help do things like reduce RF breakdown, which leads to higher gradients and power requirements and fabrication tolerances. So cooling will help with that, but then cooling has its own set of infrastructure associated with it. So that's a whole other expense and design that has to be considered. Okay, next. So use of VSim for accelerator structure modeling. VSim's an E&M and PIC plasma code developed with TechX. It's the most cited plasma code available out there. It's compatible with multiple file formats, and it scales well into HPC, which is high performance computing, which is important. And one way we started playing around with this actually a while ago, a couple of years. And one of the first things we did was build a toy model. And here we have a set of couplers, which is the way to deliver energy to the array of cavities here. And then we've moved on, and we were able to determine some of the eigenmodes. The blue is areas of less intensity, red is areas of higher intensity, and we were able to determine modes here, eigenmodes here. And I don't know if this fits any, no, this does not fit any particular eigenmode, but we were running traveling wave simulations on a Cband structure. Next, please. Okay, so two geometries were chosen, disk-loaded waveguide and elliptical cavity. The disk-loaded waveguide was created from scratch using the GUI screen, and that's what we resulted in. We ran our simulations on that, and then also decided to do an elliptical cavity, which has the shape that is shown on the bottom, and that has its own set of design parameters. So in order to get a phase advance of 2 pi over 3, so as you get the wave propagating through, at 5.712 gigahertz, we have a length of the cell that's on the order of 17 millimeters. So that's each cell, but still the whole array here is going to be much, much smaller than that's once proposed. Okay, next. So some disk-loaded waveguide passband modes. So there's a paper by Wengler on RF cavity design from 1998, which had a nice a diagram in it, which I found to be very useful. But it basically allowed us to correlate these patterns of color to different modes. So this, for example, would be a pi over 3 mode here, because we have two high intensity, 3 low, 2 high intensity again, and it gives this kind of a shape pad here. This is a pi mode because it's, you know, down, up, down, up, down, up. And that's what he indicates in his paper. And then we have a 2 pi over 3 mode. We have a field alternates by 2 pi every third cavity, and it would look something like this. Okay, next. So recall that I've mentioned before that radius is inversely proportional to the frequency for TM010. So one thing that we like to do is run some baseline calculations in order to see if VSim's working. I mean, we know it's going to work properly, but I mean, to understand that we're setting the problem up in such a way that we're getting the answer that we really want out of the question. So in order to convince ourselves that we were really doing that, we just ran a pillbox cavity, which comes as a preloaded example with the software package, which is nice. So we were able to tweak that and get started relatively quickly. But we did verify that. We've determined eigenmodes versus R over R0. And so the larger cavity core comes along with the resonant frequency decrease. So that works as you would expect it to. And we tuned the cavity for the TM, the traveling magnetic 010 mode at 5.712 gigahertz in a 2 pi over 3 phase advance, which I've said before already. Okay, go on. So these are the results in the cavity comparisons and a dispersion curve for the disk loaded waveguide and the elliptical cavity. And we can see that they are very similar in terms of the 2 pi over 3 eigenmode frequency. So that is good. We can tune them both to perform the same way. And these are the field patterns here. Okay, next. Conclusions. So for the C-band, VSim's been successfully used to determine eigenmodes in the RF cavity arrays that I've been talking about. We did publish the results in NA-PAC 2021. The proceedings have to be released, but as far as I know, they're done. We're preparing a NIM publication on an expanded set of this work here. So the next steps, we want to use the history function in VSim to determine the figures of merit of the cavity. So it's things like quality factor, accelerating voltage, field energy, peak magnetic field, etc. And in order to do that, we have to use a combination of text-based and GUI setups, depending on what we want to determine and how they were originally developed. We do a lot of things by adapting what's there already to our needs rather than trying to do it from scratch right away. But I would like to say that TechX has been extremely helpful in working with us to help us understand what we're not understanding, and write code for us is necessary. There are other projects which I'm not mentioning here. So there is that, but it's been a bit of a learning curve for us. I'd like to introduce particles into the cavity and to make sure that we're getting a good beam through there. ALCF, Argonne Leadership Computing Facility, which we'll talk about in later slides, will be used for a series of optimization simulations. This is a very important facility in the US, actually worldwide, for solving big simulation problems with a lot of data. So this is, I can't stress how important it is to problems like this, because once we start to introduce particles into the cavities and we start to make a cavity geometry more complicated, the longer it's going to take to run these simulations. So that's definitely a plus for us. For example, going back to these structures here, this coupler design, we want to perfect our use of CAD for geometry generation and adjustment. Now remember, we have a disk-loaded waveguide, which is a cylinder with like dividers in it, and we have the elliptical cavity array, and that's a series of ellipses. But in between each one of those cavities, there's something we call an iris, which is this round structure here. Yeah, and that may not necessarily be round. It could be elliptical. It could be tapered. The whole array is probably going to be tapered. We'll probably need upwards of 70 individual cavities in order to get the accelerating up to where we want it. So we have someone in the group that's working on CAD, which Sal and I have been talking to, and he's versing us. His name is Tyler, and on how to use CAD, and we have Fusion. And we also, we'd like to lean on other people with even more knowledge of CAD, obviously, but we would like to start getting more sophisticated with that part of the program, and also continue to develop procedures for characterizing fields and the different geometries. And I think that's it. So you want to go next? Yes, that's it for me. Now, Colleen, do we want to do questions for me now or
Yeah,
no?
so if anyone has any questions, they can type them. There's a little Q&A at the bottom of your screen where you can type them in, and then we will answer them, and we'll just go ahead and answer them at the end of the presentation. But I do want to highlight that it's there for people to ask. Thanks, Trudy.
Thank you.
Can you hear me?
Sounds good. We can hear you, Salvador.
Oh, this is John, actually. So I have a question for Trudy. First of all, Trudy, can you hear me, Trudy?
Yes.
Okay, good. So first of all, I'd like to thank you for that very nice talk.
Oh, thank you.
Doing really good work here. And the nice thing is that DOE likes it because you're using ALS. And so all that's really, really good. So, but I have a question for you, which is, you're now going to start on optimization. What's the first thing you're going to do? Is it going to be some scans? Do you have some intuition about what you want to change? Can you tell me a little bit about that?
Well, it'll be a combination. I think we'll start with intuition, just conversations. Sal and I have, like, for example, had some conversations with Massimo Del Forno about this, how this cavity is actually going to be designed in the end. And that's where I came up with this idea that the whole thing might be tapered and that each iris may actually have a strange shape to it. But I'm just going to have to start. I think I'm going to start with intuition and then start tweaking around that intuition.
Mm-hmm.
Does that answer your question?
Yeah, it does. Do you have any intuition on the things you're going to start tweaking?
What am I going to start tweaking?
Yeah.
I think what we're going to have to start, and maybe Sal, you can jump in here too.
Can I jump in? Yeah. So I think one of the things we want to look at the beginning is most of the C-band technology that is out there. They go for what are called constant impedance structures.
Mm-hmm.
So like, like if you see here, the cells, all the individual cells have the same dimensions, but that's not necessarily the only approach. So we want to play with modifying the kind of taper, the general parameters, like modifying the aperture as the cavity progresses, or modifying the length slightly to produce, rather than having constant impedance C-band resonance structures. We're aiming for high gradient, which maybe like you can find it on the textbooks. I'm not sure if there's any that has been fabricated, but it seems to have more, like usually high impedance, constant impedance is selected because it's easier to fabricate, and you can produce like lots of them because it's basically the same cell repeating itself. We're probably looking into a little bit like changing the cell as the beam gains energy, and that's one of the things we want to do, optimizing the iris. I think that's kind of our starting point.
Yeah,
Okay,
and
thanks
there's
very much,
probably going to be
Sal.
a trade-off between the two.
Yeah, thanks very much, guys. So, okay, so I think then what I'm hearing from you is that you're trying to get something that is such a high gradient that, you know, like if you did a traveling wave tube LINAC, you would increase the lengths of the cavities as you go to the high energy end, right? And then you have to keep it accelerating at some constant rate, and you might have to modify other parts of the cavity to get the mode profile for your pi mode correct. Is that kind of what you're thinking?
Yeah,
that's
keep it
kind of our,
traveling wave.
Yeah, that's kind
Well,
of the thing, and
gosh,
it doesn't have to be within the same structure. We can have like different types of cavities as it progresses, as the beam gains energy. That's
and
well,
then,
I think that's going to be real cool, and I really like the idea that you're going to challenge the experimentalists and the fabricators, because you know that really proves what computation can do. We can do stuff so easily and make their lives difficult. So I like that.
Yeah. Something else that is, yeah, so we care about the high gradient of the real state, but also for this mesoscale capability, you need to be able to produce complicated trains of particles like with the specific patterns to explore all these regimes. So that also needs to be somehow.
Yeah, so if you want to do a timing experiment, you need a special pattern, for example.
Yeah.
Interesting.
Also, that's another thing
Mm-hmm.
I'd like to bring up is that another ball of wax that I didn't even mention at all is the fabrication of the material that the cavity will be made of, because as you know, it gets harder to machine things in certain size regimes, and then the copper itself, depending if once you go to cryocooling, then you got to worry, you know, the copper itself has its own properties. The way you put the cavity together has consequences, you know, if you braze it, for example. So
Okay, and I have
there's
one
a
more
lot of work to be
question.
done.
I have another question, but I don't want to take away any of you know, Sal's punchlines or anything. So
I'm
if you're
okay. I
going to
don't
cover
have,
it,
don't have that many slides. So
we could always talk offline too.
yeah. So one of the great things, you know, people always, they design these things and they're always in this sort of azimuthal symmetry land, right? They make things, you know, cylindrically symmetric. And I've always wondered what would happen if you started violating that and going off into weird regimes. Nobody ever talks about that. Have you guys
How
given
weird
that
were
much
you thinking?
thought? Well, you know, it could get pretty weird. Like you could have some sort of helical structure, or that's only mildly weird. But you know, something that's, you know, asymmetric, or all kinds of stuff you could
corrugated,
yeah,
yeah,
corrugated.
I think because for accelerating cavities, you want the maximum field along the axis. That's where it comes from. But I have seen some elliptical shapes, like actually elliptical, in the other plane. Yeah, like in the azimuthal plane. For things like energy recovery, you have basically a mode that changes in the radial direction so that you can recover the energy from the beam. And yeah, like some of these geometries get really weird. Yeah, I agree.
Actually, I would like to mention that in the text-based setup for the elliptical cavity, there's this Z-squash array that I could play with, and that
Yeah.
destroys the symmetry in one dimension.
Yeah, and that was for making a crab cavity. That was for separating
Mhm.
the vertical modes, right? The two n=1 modes. Yeah,
Yeah.
that was one of my little inventions. So anyway, okay. So, and then I got one more question, because the more I talk to you guys, the more questions I have. You're going to be operating at high gradient and perhaps high current. And so then I'm wondering, do you worry about higher order modes and, you know, beam instabilities that might be created by that?
Beam instability, definitely. I would, higher order modes, I'd have to think about.
Yeah, I know that's been a big problem at JLab, so I was just curious where you guys might be going.
What, yeah, okay. Well, we can talk about that offline.
Yeah, I'm monopolizing too much of your time, but I just think you gave a really interesting talk.
I think, yeah, at some point we need to, once we finalize on a particular geometry, then we'll look into HOMs and all these things. Yeah.
Yeah.
Okay, great. So we're going to be working in that area too, so it'll be good to talk.
Okay.
Great.
Well, and if you, while we're asking Trudy, we did receive one more question for you, Trudy, which was, how large is the Q value for this cavity, for your cavity? Is beam loading the main factor in determining total Q?
For this factor, we get inverse Qs out of eigenmode determination, 10 to the -6, 7 sometimes.
Yeah,
Q.
but I don't think we have started doing like beam calculations for these structures.
Yeah,
we've been
haven't
focusing
rigorously.
on the modes. Yeah.
That's a typical value that we get read to us from the analysis in the software.
All right, thank you.
Thanks.
Okay, well, then I can probably start talking about my section.
Yes,
So
go for it, Salvador.
I'm gonna talk about, so I like to think as the Cband and that Trudy is working on and the RFQ that I'm working on. I think these are kind of a research group, like VSim flagship projects. So these are the ones that we've been working on a little bit longer. So mine, well, I'm going to talk about a different accelerator, which is called radio frequency quadrupole, or an RFQ for short. And we've been using VSim to do these simulations, and also HPC, which Trudy mentioned briefly. So this is a completely different type of a particle accelerator. This actually has already been built. So our simulation focus is on a different of a different nature. So let me start by describing the machine a little bit. So our collaborators at ILS, Ion Linux Systems, they are developing compact, affordable accelerators, particularly for medical applications. So this is a picture that I took of the machine as it stands. So it's formed by a ion source, which is an electron cyclotron resonance ion source, which is this part here. Then there's a series of magnets that help focus that initial beam, and then there's the radio frequency quadrupole here. So they are developing this particular machine for something that is called boron neutron capture therapy, which is a type of non-invasive cancer therapy. It uses neutrons, a beam of high flux neutrons with a particular energy to attack the cancer. So basically, and this is the part that I'm not 100% sure, like the biochemistry of it, but they use some sort of a boron tagger that attaches to the most metabolically active cells which tend to be like the cancerous cells. so the boron attaches to them, and then when you irradiate it with a neutron beam, the boron captures that neutron, and the resulting nuclear reaction releases alpha particles, which decrease within a cell's length, effectively just attacking the cancer and not the healthy tissue. So that's a very cool feature about it. And because you don't have to target the beam into the actual cancer region, because that's already defined by the boron, you can produce a significantly larger neutron beam profile that kind of shines in the region of the cancer, but it's only affecting the cancerous cells. So it's a neat approach, I think. It's not a new concept. It has been used for decades, but mostly using neutrons coming out of nuclear reactors, which tend to have a broader energy band, and that's not as efficient. So this is attempting to do that nuclear reaction more efficient. And also, yeah, this is a compact machine that can be, as you can see, like this is pretty much it. Like that's all the infrastructure. It fits on a room. It's very and most of these technological developments are aimed at making this technology cheaper and easy to use, something that you can set up in the basement of a hospital without needing like an extra building to support it or something. So they have a proprietary type of accelerator, which is called a radio frequency interdigital. And this is what enables it to be this short. The full machine is about like 5 meters, like it's really compact. And our collaboration with UNM, it focuses on developing controls for this machine, which one part of making the machine cheaper is that you want it to be easy to operate. Like you don't need, ideally you wouldn't want to have like a highly skilled operator. So we're trying to develop controls that allow to do that. So this is kind of what the RFQ looks like from the inside. It is a copper radio frequency resonant structure that operates in the 200 megahertz. It has 4 electrodes or vanes that, as you can see, they are tapered to produce some energy gain in the beam. And this is actually a really cool structure, I think, because it's doing several things as the beam comes in. So the beam coming out of the ion source, that's a DC beam. It's just a continuous stream of particles. And then the RFQ kind of captures that initial beam. And because the ions are traveling at a relatively low energy, you can use electric fields to focus them. So these vanes kind of focus the electric fields along the axis. They produce some sort of focusing, but also in the middle region of the RFQ, you also get some bunching effect. Once the particles that are on phase with the electromagnetic field, they're gonna have the most energy gain, versus particles that are off phase, they're gonna pretty much stay or not gain as much energy. So it captures the beam, it does some bunching, and once you have the bunches, you have some acceleration as well. So it's a compact structure that is doing all these 3-4 processes, and then it delivers the beam to a more efficient, usually to a more efficient accelerator. But this, for low energies, this is very this is ideal. Like it gets, I don't think it gets too much better than this for low energies. And this is, we usually start with a beam that is 35 kilo electron volts at the right side of the RFQ. And by the time it exits, it's already bunched and it's at 750 kilo electron volts. So it's a huge energy gain. but yeah, so we're using VSim, mostly the electromagnetic and the particle in cell solvers. We've been using geometries that we import from CAD. We've been using the prescribed field associated tools. We've been using particles and many of the analyzers that come with the code as it stands. And also, yeah, we've been using VSim on our high performance computing system at the Argonne Leadership Computing Facility, which is called the Teta Supercomputer. So we run most of the simulations there just because it's faster. So for this particular problem, I'm using about 30 million cells to get like good resolution within the veins and for the beam traveling inside the axis, the beam axis. And yeah. So using the electromagnetic solver, I was able to determine the fundamental mode of operation, which you can see here. This is the longitudinal electric field inside the RFQ. You can see the boundaries of where the veins are standing. And yeah, most of the electric field is concentrated along the beam path, which is where we want it to be. So yeah, this is how it looks like. You can kind of separate again the regions where you're capturing the beam, where you are producing some modulation to punch the beam initially, and then where you are actually getting the greater accelerating kick. So this is the eigenmode, and we also scale it to the power loss that is being dissipated on the surface of the RFQ, which we took to, which is again, it's copper. So that's how I've been scaling the power in these electromagnetic fields. Some of the calculations are in good agreement with previous simulations before we started using VSim, and also most importantly, it's almost one-on-one with experimental results that we have. So that gives us a lot of confidence. And so basically, because this machine is already modeled, it's already built and it exists. What I've been trying to do mostly is try to replicate the observed behavior. So I'm trying to tie the simulations to the actual measurements so as to be able to do some machine learning with these simulations. So yeah, we have used the electromagnetic solver, and we've also introduced particles into the RFQ. Here's some of the observed beam dynamics. So in the first sections of the RFQ, we get some focusing, which because we have an RF field, it's alternating. So we have an alternating focusing in the vertical and the horizontal directions, as you can see here, for different time steps. So we're getting some sort of, we're getting the alternating focusing that is expected. We are getting this kind of a cartoon picture, but the initial beam, we're using a uniform beam to begin with. And you can see like the overall effect at the end of the RFQ, which are the blue dots. It's an overall, yeah, like the beam is being focused, which is one of the objectives of the RFQ. But most importantly is the longitudinal beam dynamics, because we want to be able to produce the right energy. And this is important because so as I mentioned at the beginning, and I don't know if anybody not familiar with accelerators picked up on this, but for the cancer treatment itself, we need a beam of neutrons. But neutrons they don't have electric charge. So how do you accelerate them using electric fields? The reason is the answer is you don't. What you do is you accelerate a beam of protons, and then you make those protons interact with a target, which is, I think, tungsten, like a heavy tungsten target. And then you get the neutrons out of the spallation process. So you want these protons to have the right energy that you are actually able to produce neutrons. Otherwise, the whole endeavor is like, yeah, you're not going to produce the neutrons that you want. So the RFQ deals with protons, and they need to have the right energy. So the longitudinal beam dynamics is important. We need to be able to show that we produce the bunching and that we produce the right energy. So in this figure, I'm kind of just showing the whole beam as it progresses along the RFQ. So the beam starts at the left side of this diagram, and then as it progresses, it just starts getting accumulated into little pockets, which they are on phase with the electromagnetic field. And because the fields are scaled properly, we actually get the output energy that we observe on the machine. So this is good. We start with the energy that the initial gun produces, which is 30 kilo electron volts or 30 kilovolts. That's the voltage that we apply. And then we end up with about 750 kilo electron volt protons. And yeah, so that's kind of just modeling what we already see on the machine. But the really new thing about this research is we're exploring the use of what are called surrogate models of in this case, of the RFQ. Because we want to be able to produce control so that like a technician at the hospital is able to just push a button and get the beam into the patient. So we're trying to use as many tools as we can, and one of them is the use of AI, artificial intelligence, in support of some of the control tasks. And one of the ideas is, well, this simulation is very realistic. It has all the it accounts for all these details of the actual device, because maybe you don't have an analytical expression that you can readily use. So the simulation is very powerful in that it gives us a very what I call a physics detailed kind of a screenshot of what's actually happening inside the machine. So we want to be able to use all that information to feed the controls in a more efficient way. However, running this simulation as the one that I showed you in a workstation, it takes doesn't take a long, but yeah, it takes a few minutes. So it's probably not good to be used in a real-time environment where you want to be able to change the set points of your instruments like every, I don't know, like every second, for example. Like it's just too slow. So it's too slow, but it also has a lot of detail that we want to use. So one thing we're exploring is, well, maybe we can come up with a surrogate model, which is basically it can be built upon any machine learning algorithm. We're starting to use a neural network to do that. And the idea is basically, well, this simulation is valuable for us. We want to be able to use it almost in real time. So we're trying to kind of code that simulation into the appropriate weight values of a neural network that it actually accurately reproduces what we see on the simulation, which is also what we see on the experiment. So that's kind of the idea. The trade-off is, of course, if you're familiar with neural networks, you need to present them examples of what you expect them to do, and these need to be good examples. So the trade-off now is, well, we need to be able to run this simulation for potentially thousands of different case scenarios and make the neural network learn all those observed behaviors. That's kind of where we are heading. In that sense, yeah, we want to turn the VSim simulation of the RFQ into a sort of a quick lookup table that you can easily program into an FPGA and use for the controls of the machine. And that's kind of where we're heading. Now, yeah, like if this simulation takes, I don't know, like 30 minutes to run on a regular computer, we probably need to find a faster way to do it in order to run potentially thousands of different scenarios. And that's where using the Theta supercomputer at Argonne National Lab, it comes into play because, well, this is a very powerful system. It has about 280,000 cores. Well, yeah, and we can basically use, we already have VSim deployed on this system thanks to John and TechX. So we've been using VSim here. We currently use it for electromagnetic simulations with VSim, particularly on the RFQ, doing some of the optimization tasks that Trudy was describing. And also, right now, we're also using it for some AI and machine learning in different projects. So we use this system for many things. Particularly for this simulation that I just talked about, we did some quick optimization where you can see like running this problem in the laptop where I'm like streaming now. It takes about 180 minutes versus our workstation, which is about, it's about an hour. And you can optimize Theta, like all these flags that you can play with to kind of bring it down to about 10 minutes. So that's, yeah, if you start with one simulation per hour on our workstation versus one per 10 minutes, and this is only one allocation, you can have multiple allocations running at the same time. So that's how we're trying to get these training examples for our neural network. Right now, we're starting to produce, like, we pretty much have the baseline simulation set up, and now it's just going to be a matter of kind of mass produce data given that simulation. That's kind of where we're standing right now. And I think, yeah, that's kind of where our talk ends. So we have some acknowledgements for our funding agencies, mostly the Department of Energy through this contract and through the Argonne Leadership Computing Facility for the resources, as well as Element Aero for the workstation. So that's, I think, yeah, that's kind of what we have. I don't know.
Well, thank you, Salvador. If anyone has any questions, you can type them into the Q&A. Hit the Q&A button on the bottom of the screen and type them in, and we can answer them. While we're doing that, I just want to mention that if you've never worked with VSim or you don't have our most recent release, you can go to the TechX website and you can request a 30-day evaluation of the software with all 4 packages. So all of the capabilities are in there, and allow you some time to play around with the software and see if it's something that might work for you and for your problem that you're trying to solve. Let's see. Looks like we just got another question that says, so for the runs with 30 minutes, those ones were performed on what kind of machines and how many cores?
The runs for 30 minutes. Do you mean these ones here?
Let me see. I see your, yeah, it just said the runs with 30 minutes were performed on what kind of machine?
Yeah, so, well, if that is the question, yeah. So we use all the points below this dotted line. Those were calculated on Theta. Okay. The difference is we use different number of ranks, or basically the number of processes that you are running simultaneously. So basically how this reads is we take that VSim problem and we partition it into 128, and that gives us about 40 minutes into 256. That gives us 25 minutes. 1000, what is it, 24? That's about 10 minutes. That's how you read this. I don't know if that was the question.
Thank you.
But yeah, and then yeah, like the particular processor that this machine uses is an Intel Xeon Phi.
With just a few cores, I see.
Yeah, just a
Just
tiny
a
bit.
couple.
Very cool. Any last questions?
Well, I always have a few, if you don't mind.
Go ahead, John.
So, you know, you're doing these simulations with the ultimate goal of creating something for cancer therapy, i.e. radiation therapy. And so at the end, you probably want to take what comes out of this and throw it into something like a géant, which would allow you to propagate your high energy particles through, you know, a collimator and whatever it takes to put it on target on the tumor of the patient. So that means coupling of basically VSim and Arson. And I know, I don't think you've tried Arson yet, but maybe, you know, you'd be welcome to try it. But my question really is maybe oriented towards, once you do give it a try, what's missing to make this easy? I mean, Maxime was doing that this morning too, right? Maxime was creating high energy particles and then propagating them through materials. And so now you're doing it this evening. And what do you need? What do you need to get that done?
Well, I don't think we've actually deal with the target a lot, but yeah, I think Arson would probably be a great tool to.
Well, wait a second, says the
Okay.
materials person here.
Okay, go for it. Yeah.
Yeah.
Sorry. I've actually been mumbling the word arson a lot because I think there is, especially for things like photocathodes or coatings on cavities, you know, arson might be pretty useful because it's all scattering and radiation interactions, and so there might be a way to use the results from an arson calculation and overlay them with the results from an accelerator or plasma calculation, and
Yeah, so I guess I'm just
get enhanced data sets.
I guess I'm just asking you to think about whether you want some sort of whether that's something that you can sort of do through a loose coupling. One code generates a file and goes to the other, whether that would not be fast enough. We're obviously going to pick your brains pretty seriously, so, you know, put your helmet on.
Okay.
So we'd like to hear what you have to say.
And for
Okay.
those of you that don't know what they're speaking about with Arson, Arson is our radiation modeling software that we have that you can also request a 30-day evaluation on from our website.
So then I have one more question. And that comes back to you, Sal, which is where you said that what you'd like to do would be to launch a whole bunch of jobs at different values of parameters so that you could start getting results that you would then feed into your neural network for it to learn on.
Yes.
Now, if you're going to do that, I have then sort of two questions, which is, of course, you guys are, you guys know enough about computing that you could probably write some sort of a Python script or Bash script to do that. But when you do that, you would be probably saying to yourself, well, you could imagine a bunch of different ways of doing that. You could say, well, here's my big n-dimensional parameter space, and I'm just going to scan it, 10 points in the X direction, 9 points in the Y direction. Or you could say, really what I'd like to do is I like to pick a couple of points here and there and maybe take a generation and figure out where it might be best. And narrow in. Have you guys given much thought to the kinds of things you'd like to do as you generate data for your neural network?
Yeah, so one of the things we want to do is not, like sort of when you do a scan, you kind of have like we don't want to introduce a correlation there. So we want to kind of randomize all these variables within yeah, within the actual space that they can live in, like the values that they can take that are realistic that we see on the machine. Yeah, so we kind of want to, I think we made a kind of an inventory of our parameters, and it came to about like the way it's set up right now, like about 10 different things that we can change as an input. So we want them to be as random as possible. Like we don't want to introduce like we want to be, yeah, like we want to randomize all those 10 and choose a random value each time that we feed, and then that's going to be one case scenario. And then we take a different new random value from all those 10 inputs and see what happens. And that's kind of what we're trying to do. Of course, some of them are more sensitive to the beam than others. So yeah, that's kind of what we're thinking, how to approach that, because you don't want your model to learn that correlation that you may be introducing without realizing. And it's also not random by itself, because we have done some experimental, like we've had some dedicated beam time running the machine and playing with the actual, like literally the actual knobs on the power supplies, and see how that changes the beam. I actually forgot to put some pictures, but we have some pictures of how the beam looks like. And of course, it's not a uniform beam, right? It has some distribution. It's not symmetric. It has all these features that we want to be able to put there. So yeah, I mean, it's probably gonna be more than 10 variables that we can change. But yeah, we just want them to be a little, yeah, like just random, like not correlated to each other.
Yeah, but that could be a little difficult. I'm thinking because some of the things that can happen are coupled in reality.
Yep.
And you just can't get around it. For example, if the cooling water stops flowing, you get a temperature rise, but nothing you do to the rest of the machine is going to help until you turn that water back on. You have the wrong flow rate on the water. You can introduce vibrations into the so.
Yeah, and the problem we're facing with feeding these systems for AI controls is that you need to be able to have a lot of like feedback from the machine, like a lot of instrumentation telling you what's the real status of the machine, but a lot of these things are not being recorded in the way that we would like to, or they are like, I don't know, like you get the frequency of the resonator every so often, or the temperature every second, and that's not, it's a lot of, yeah, it's a lot of things missing. But that's kind of what we're thinking and where we're heading. And yeah, I don't know if that answered the question.
Yeah, no, it did. I think it sounds like it's still an area of research, and so that's good. You know, research is how we make a living, after all, so that's good. But thank you very much. And Sal, I really enjoyed your talk. You did a really great job.
No, thank you.
All right, I think that is it for the questions that we have. Unless anyone has anything else that they want to type in real quick. We have one more talk for today coming up in about 30 minutes. We're going to have Ming-Che Lin giving a presentation. So we're going to pause this for just a bit. And if you want to come back in just a few, we will have our last talk of the day.